Now let me give you as a special case an example to how one works with orthotropy and how it arises. And let us remind ourselves that orthotropy requires ultimately 9 independent constants to characterize the compliance matrix. And my discussion is an idealization of a practical situation and a generalization of it so that we understand the qualitative features associated with orthotropy. So the starting point is going to be simply a cube of a isotropic material. So that isotropic material is going to serve as the starting material from which we're going to construct a composite. This material, in the context of many composites, in particular for those that are employed widely in aerospace and automotive engineering structures, it's a so-called epoxy material. It's a polymer. It's a thermosetting polymer. Thermosetting means when you heat it up, that hence the name thermo. It sets. It retains a permanent shape. Okay. So initially it's soft. You can easily deform it into a shape you want, and then you bake it. You heat it. Making composites is like baking, and then it will retain that shape, and then you take that complicated shape and put it into a certain application. Epoxy is a polymer that is actually isotropic, okay, before you do anything to it. So now, however, what we're going to do is we're going to go ahead and enforce this polymer with certain types of fibers. A fiber is essentially like this lead from a pencil, or essentially a thread that would run in any textile clothing. Eventually, it's a thin, long structure which may or may not be very strong under tension. They are usually very strong under tension, but because they are very thin, they are not so strong under compression. So if I have a lead pencil, for instance, lead pencil input, right? And now, if I try to pull on it, then it can carry a large amount of load actually. But if I try to compress it, it's very sensitive because the very slight amount of imperfection you might input into the structure will cause it to technically buckle, which is a concept that eventually is covered in ME 231. It will buckle, so in other words, it will quickly bend out of shape under compression, typically all the way onto failure. So if I'm pressing, and now it has a very ideal shape, but the thinner this fiber is, any amount of tiny imperfection will quickly cause it to break under compressive stresses. The reason it broke is because that bending is something that quickly imposes very large tensile stresses. It's such a thin structure, the stresses are immense, and immediately the structure breaks apart because carbon, for instance, fiber is quite brittle. But if you were to put it into a epoxy matrix, that epoxy matrix would sort of stabilize it from bending out of plane towards in the transverse direction. So it would also be stronger under compression. It would be stronger if it is combined with epoxy, and that's the idea of combining two materials when you make composites. When you make composites, you're sort of combining best of both worlds. There is a material that is isotropic, so it has the same type of behavior along tension, compression in all directions. And then into it, just like sticking a candle into a piece of cake, suppose you now stick in a lot of carbon fibers. Those carbon fibers are now schematically, they're running along that direction. And what you do is, you are strengthening this structure now, building a different structure, a so-called composite structure that is neither carbon nor epoxy, and it has a much higher strength that is closer to the strength of the fibers in that direction. Not so much change of strength along that direction, but still when you compress it, it can also carry significant amount of load, but because now that the fibers are surrounded by the epoxy matrix, it's called a matrix. the surrounding material, the carbon fibers cannot easily buckle out of shape and break under compression. So the fibers, they can help us build a composite material. In this case, formed from a fiber plus a surrounding matrix. So now we can keep doing this in different directions as well. So for instance, in the other direction, along that direction, I can stick in different types of fibers. Now in practice, you wouldn't do this really, but suppose I stick in fibers, different fibers along the other direction, and let me call those Kevlar fibers. Okay, so green is Kevlar. Red, I've already noted, it is carbon. And Kevlar is a polymeric textile type fiber. Because it's textile, it has absolutely no strength under compression as a thread, as a fiber thread, but under tension it can carry a lot of load. But once you put it into something, then together with the epoxy matrix, it can also possibly carry some compressive load. And finally, you can have fibers running in the other direction, in this case that direction, and let's call that those glass fibers. They've been employed for a long time, and so what we're going to do is we are going to stick them along the remaining axis, and they are going to run in that direction. Okay, so those are the glass fibers. So we can call that direction the X direction, this one the Y direction, and the other direction the Z direction. Okay. So now we have X, Y, Z axis, and I'm just wondering now how I can characterize this material. I'm only interested in the elastic behavior. Now I can already see perhaps that the strength along each direction is also different, and each strength along every direction is different from the original strength of the epoxy and also of the fibers. And the same thing goes for elastic properties, but here we're only concentrating on elastic materials. So likewise, the Young's modulus, say, along that direction is going to be probably different from that and different from that, all of which differ from the Young's modulus of the epoxy matrix and of the fibers themselves. Why do they differ from both? Well, because if you put just a single fiber, a micrometer diameter, and this cube is, let's say, of size 1 centimeter, that one single fiber is not going to have any influence. So the amount of, let me say, fiber you put in is important. If you put very little, the stiffness is not going to increase much. If you put a lot, it's going to increase a lot. But you cannot put a lot because it's like mixing dough with water. In this case, water is like the matrix and you put dough into it. But a certain amount of water can only hold so much flour, right? If you want to make dough, you can mix water with flour. For a given amount of water, you can only put so much flour into it to make the dough. Otherwise, the dough cannot remain intact. It will just crumble into pieces. So here as well, you don't want to put too many fibers. You won't get structurally a sound composite out of it. And as soon as you cannot put 100% and less than it, then the amount you put will influence how much closer you get into the modulus of, say, carbon fiber. When you put more and more carbon fibers, the more you put, you approach the modulus of the carbon fiber along that direction, but you cannot put 100, so the amount you put does influence the result. The final result is neither the modulus of epoxy nor the modulus of the carbon fiber. That we should keep in mind. Exactly how the amount you put in influences the outcome is a task on its own. You can take a course, elective course on composite materials. There, the methods of estimating the resulting Young's modulus for a given combination and amount of fibers and matrix, let's say, these types of topics are covered. In your book, there is a small discussion. In one of the homework problems I have also assigned, such a small analysis is also required to give you an idea of how to predict the outcome of a combination of two materials in terms of Young's moduli and in fact Poisson ratio. So presently we're just qualitatively concerned with this combination and the type of elastic behavior that it displays. So that elastic behavior is characterized through the compliance matrix. And that compliance matrix is going to have, as usual, normal and shear, as well as normal shear and shear normal coupling parts. So here we have NN, here NS, here SN, and here SS. Now it is symmetric, so that part and that part, they are equal to transposes of each other. That's the correct way to put it in terms of matrix terminology, or let's say 4, 5 would be equal to 5, 4 eventually. For that reason, I will only write that part. It's going to be symmetric. And here I should point out that, remember, I said that when you have anisotropy, in general, there is normal shear coupling. But that's not a necessity. That is a possibility. It turns out that the axes, the choice of the coordinate system with respect to which you are writing the stresses and strains, and ultimately writing the relation between them through, therefore, this compliance matrix, they all depend on the choice of the coordinate system. So we're going to see in our next topic that for a given state of stress, if you choose different coordinate systems, the same state of stress will have components that appear differently. The values of normal and shear stresses will seem to change. And that change is occurring because although you're describing a certain state of stress, which might have to do with, let's say you have a beam and you are bending it, and at that point there's a certain state of stress and you're interested in writing it with respect to a coordinate system which may or may not align with the axis of this beam. So different choices will lead to, it turns out, different expressions for the stress components. So here as well, those components of stress and strain, they will be related to each other by the compliance matrix. And the choice of the coordinate system will influence the way that matrix looks. Presently, for an orthotropic material, I've chosen a coordinate system that aligns with the fibers. Because they align with the fibers, it turns out that the off-diagonal components, block matrix-wise, they are identically zero. So there doesn't appear to be normal shear coupling. Why? Because it turns out I've chosen my axes to align exactly with the fiber directions. I'm going to give you an example in the future, and I'm going to show you that if you change either the orientation of the axes, x, y, z, so instead of choosing them like this, you choose them at some other orientation, or this is still x, y, z, but the fibers don't run like this, but at a certain angle with respect to the coordinate directions, these are not zero anymore. And then you will get normal shear coupling. So having non-zero terms here does not imply that the material is, let's say, isotropic. Certainly doesn't. I have to check many other things. In particular, it doesn't mean that the material does not display normal shear coupling. It just says that for this type of coordinate analysis, for these types of coordinate directions that I've chosen, that there is no normal shear coupling. It will become probably more clear when I give you an example in the future. So we have the setup of the compliance matrix, and I already have told you that these off-diagonal components are equal to 0. So let me go ahead and first tell you what the remaining components are. Well, to do that, I have to look at the individual planes as a means of motivation and just observe certain qualitative features. And what I'm going to look at is, for instance, the z, y plane. And then I will have a look at the zx plane. And then I will have a look at the xy plane. So that is zx. And then this is going to be the xy. So I'll complete the picture. That's okay. So if I look in the ZY plane, it's that plane, I see fibers that run in the red and green directions, but so red and green direction, there are fibers that run within the ZY plane, and the blue, the remaining fiber, is running out of plane like this. May or may not be ordered. Now for ZX, in the ZX plane there are glass fibers and Kevlar fibers running. I'm not drawing them, but out of plane direction there's the remaining carbon fiber. They run out of plane. Okay. And in that last picture we have out of plane direction as being the Kevlar direction. So now if I shear this square, I will be trying to change the angle between Kevlar and carbon, and in between there's some glass. So there will be some shear modulus associated with that. If I want to shear that picture, I'm going to be shearing not Kevlar and carbon, but Kevlar and glass. So there's going to be another shear modulus probably, and they're not going to be the same. Out of plane direction is also different. Here it's glass, here it's carbon. And in that case as well, it's still yet another combination of fibers. Here we have carbon and glass. Out of plane direction is Kevlar. So if I shear these two directions, it's going to be different again from this one as well. So each shearing will have to do with its own set of shear moduli. So remembering the order, this one is going to be a shear modulus that sends a shear stress to a shear strain. And so it is YZ, that's the first one appearing. The second one is ZX, so it's 1 over GZX. And the third one is going to be 1 over GXY. Okay? And it turns out that, again, because of the orientation of my coordinate system or of the carbon fibers with respect to this choice of the coordinate system, the out of plane components here, out of diagonal components are 0. Okay? Again, doesn't mean that there is no unusual situation. Indeed, there is an unusual situation because these are in general different from each other. Why? Because every fiber has in general different properties. Again, remember that this is a very hypothetical scenario. You would unlikely be using so many different fibers in this setting in the manner I described by sticking them through some epoxy matrix, but we're just imagining that that's the case. Okay, so then we can also think that because of the fact that strengthening along every direction is going to be different from the other one, the Young's moduli in each direction, they are different from each other. So there's going to be a EZ, EX, and EY. And that's the way they are ordered, right? And finally, we will talk about Poisson's ratio. So in other words, for instance, the amount of strain you measure along the Y direction when you pull along the X direction. You pull along blue, which is glass, and extraction has to do with contraction, has to do with carbon. Or you pull along blue, contraction has to do with Kevlar. Or you pull along carbon, contraction has to do with Kevlar. All of these are different, essentially, combinations of materials, and therefore you expect the Poisson ratio associated with them also to be different. And therefore the off-diagonal components of the normal coupling block matrix will also have shear moduli that have explicit indices that indicate along which direction you're pulling and along which direction you have the Poisson effect, the transverse strain forming. And so I will indicate, for instance, this one to be minus nu yx, and instead of E, we divide within the definition by EY. And this one is going to be minus nu ZX, and we divide by EZ. And in this manner, this is going to be minus nu ZY, and we divide it by EZ. And this one here, it's minus nu XY divided by EX. And finally, minus nu XZ divided by EX. Minus nu YZ divided by EY. Okay. Good. So I told you why I expect different constants to appear, and I've told you I've given you the general form of the compliance matrix. So now we think about this form, and in particular we think about how many independent constants I observe here. Of course the answer is supposed to be 9, but let's count. First of all, I have 6 blue components. The shear moduli are not anymore related to the Young's moduli and for that matter to the Poisson ratios, because now they are independent constants in the case of orthotropy. So 9 blue components, they are all independent from each other. So then there are the off-diagonal components. And EY, EZ, EX, eventually IC in these off-diagonal components, they are already appearing in the diagonal components of the normal coupling block matrix, and therefore I know them, so the unknowns will have to do with the Poisson ratios. And I see nu yx and nu zx, or I see nu xy and nu yx, nu xz and nu zx, right? So terms switch, right? So my question is, well, are these all independent from each other? So in other words, do I have 6 plus 1, 2, 3, 4, 5, 6, a total of 12 independent constants? It contradicts what I said earlier. And so the question is, well, where am I making a mistake? So if you think about that correct question for a few seconds, you remember that always the compliance matrix is symmetric, which you have to remember. And therefore, the two terms here, these, for instance, they are equal to each other. These are equal to each other, and these are eventually equal to each other. Okay? So notice we do not have the Poisson ratio nu yx equal to nu xy. We have that minus nu yx over ex is equal to minus nu xy over ey, as an example. Okay, so that we have to keep in mind. So if you do the counting therefore carefully, you need the 6 blue terms and then only 3 of the Poisson ratios. That gives you a total of 9 independent constants as is required. Alright, so that is a discussion of orthotropic material behavior. So next we'd like to go ahead and solve a simple example based on that.